Mason is back, and today I'm going to go over yesterday's doings, because yesterday there was, and still today there is no internet because there was a big storm, so I couldn't upload. But I have connected up everything and made the NAB, so the enable for the PLWB, and the motor 2, motor 3, motor 4, so the other wires have been connected here. These are these three, and I have the pot meters future pin that is already printing and almost done. I have to assemble it, and then I can use it and screw it here, and this will be replaced. Probably we'll have to add like a pressure sensor wire as well. Done the labelings as well here, so that there are like multiple labels, and I have started to think about the how I'm going to solve these, and today I'm going to get after that. So this is the lever shifter which I have talked about previously. This is basically for to communicate between the ESP based R32 Amos D1 R32 and the Uno. Basically this is a 3.3 volt base logic that is a 5 volt base logic, and they can't like communicate because this would be fried because of the over voltage. So this does that. This basically converts the 5 voltage signals and converts it to 3.3 volt signals, which this board can now finally like understand and not get fried with, and they can communicate. So basically I will share the load between this and that one. So what I have thought about is that this will do the PID control in the future, which we'll be talking about in the later videos, but that means the proportional, integral, and derivative gain control, and that is to basically adjust the flow valves and the heating amount and the burner's temperature, whatever, all this stuff based on the GUVA sensor readings, which are proportional to the SO3 converted from SO2. And based on that and the temperature, probably we'll do the PID, which is that this is the base value, the input. The output will be the SO2, or this is the output, the GUVA sensor readings, thus the SO3 converted from SO2, and the input will be the amount of air supplied and the heat through the coil and the power, and basically that will be controlled by this. This will set and calculate the needed amounts based on the current ones. And to be able to do that, the GUVA sensors will be connected directly to this. That will free up for us 4 analog pins, because we have basically 0 left. We have 4 analog pins, or we'll have 4 analog pins, but we'll need to take out 2 for the communication between this and that. So we'll need 2 analog pins there, the 4 and 5, A4 and A5 analog pins. Those are the I2C or I2C communication between the 2 boards, and this will be the master and that will be the slave, meaning that this will determine the set amounts and the needed amounts based on the PID that it will calculate based on that, and that will like do the thing. This is the brain, and that is the muscle for short, that will control the pot meter and the motor and all those stuff. After that done, for now I will I've been thinking about this and looking up how I should connect this, because I have no fucking clue about that. So I have done the research today, and we'll do that today. Yesterday, what I have been doing, let's put this down. What I have been doing is that I have shown you the day before yesterday that the water is flowing back from the absorber tower here, and I have used this line, but I couldn't test it. It turned out yesterday that I couldn't. The system was working fine. The main problem was that the liquid came in faster than it was like flowing out, because the pipe is pretty like small in diameter. So you won't probably be able to see it because it is so deep in there. But you need to imagine that there is like a T-joint, here's the jar, and here's the connector, and I have added a T-joint here, and this is the pipe. This is this black line that goes into the top of the T-joint. There is a connector to the leveling off, so, and there is a connector down here that connects to the line. So this is liquid basically. When the liquid is here, it sucks the liquid from here because it has lower resistance. When the liquid level goes down below this, it will suck the air up, and because now it doesn't work that well, because it will rather suck the air. It still does suck the water back from there, so that works fine. But there is air in here, which is not good for the pump because it can cause like cavity and other sorts of problems. Brine dry, all that stuff, so that's not good. For that, I will, after I have done the flow systems printing, I will connecting all these wires, figuring out the E square or I square C, whatever. I will start to design a float, basically like that there is like a T-joint here, and going to be a float here, probably going to switch up the direction, so it's not going to be like this, so it is opposite to this, but we'll draw it like it's going to be like this, and going to be, this is the top connector, this is going to be the pump, this is the sorry, this is this, and this is this. So this comes from the leveling line, this is the pump line, and this is the jar. And here there will be a float added. This is like a plug that can be like that it's like mounted here, and there is going to be a float that's going to like cause it to either as it goes up or down, it will cause it to either go back to its place, so it will seal, or go up with the water level as it increases, and then it can open and suck the water in. So when the water level is low down, the gravity will pull this down and it will close the valve, and then this line will be the main suction port from the level line, and then the pump can suck without much air or any air, if I see it well. That's the plan, at least, because this definitely will need to be put in, because so this is probably the easiest method, and yeah.